We talked a little bit about the Riemann sum, the left, the right, and a midpoint approximation. So now we're going to see how this ties in to something that is called the definite integral. So we are sort of shifting into finding approximations and now finding exact values for areas under the curve. So over here, you'll see, and it's probably been a minute since you've used sigma notation back in pre-calc, where if I am using a right-hand sum, and you remember that x sub 0 is my a, and x sub n is my b term, followed by x sub 1, x sub 2, and so on and so forth. So you'll notice that the right-hand approximation, your index here starts at 1 because it would start at x sub 1 for the right, because you're going to use the height to the right, and then it goes to whatever the nth term is. And here we have our base and our height. So that sum would just be f of x sub 1 times delta x plus f of x sub 2 times delta x plus, and on and on and on. Whereas with a left-hand approximation, we would use the height to the left. So in that case, your I would start at 0. So our index here, we would go to 0, and then we'd end in the second to last x value. And we still have our base and our height. So these are just representations of what our right and our left-hand Riemann sum look like. There is not one for midpoint. But now the question becomes, you'll notice here, if we look at the first Riemann sum approximation, that looks like a pretty decent approximation. But what happens when we increase the number of rectangles? And I'm hoping that you see, well, that's an even better approximation. And look at this one. Good grief, that is really good. So what if instead of my n being 10, 20, 2,000, what if we let our number of rectangles approach infinity? Oh my gosh. So here comes our definite integral. So here we go, bringing back limits. So if we took either the right or the left-hand Riemann sum approximation, and for both, if we let the number of rectangles approach infinity, that takes us from an approximation to an exact value of the area under a curve. So we are now using for that a new notation, and that is our definite integral. So here are a couple of things, and I've identified what is different in this. For starters, we're no longer using sigma. Sigma is going to be replaced with this elongated s, and that, folks, is our integral. And the s still stands for sum, but it's the sum of an infinite number. Next, you'll notice here, there's a lower limit of this summation notation, and then there's an upper limit. But you'll keep in mind that the lower limit, when I is 0, well, x sub 0 is my a. And the upper limit, like in this case, the upper limit is x sub n. And x sub n is my b term. And I hope that you're also just appreciating the fact that when we let the number of rectangles approach infinity, the left and the right-hand Riemann sum are equal, and they both equal the definite integral. So we're now replacing the I going from 1 to n, and we can write our a to b. A represents our lower limit of integration, and b represents the upper limit. So that's pretty much saying the integral. We're taking that definite integral from a to b, and we're replacing f of t sub I with just f of t. Lastly, this delta x, or delta t, this delta x is being replaced now with just dt, or dx. Sorry, I've been saying f of x. So that still tells us what the independent variable is. That dt is still saying for every small change in t. So let's break this down so we're clear vocabulary-wise what these things are. And I have them already defined. The actual symbol, that elongated s, is our integral. A and b are the limits of integration. A is our lower limit and b is our upper limit. Our function is in my face, that's f of x. Inside the definite integral, it's referred to as the integrand. I don't think after this you'll ever hear that again. And then every integral is sort of closed, like a period, with dt or dx or whatever the variable is that the independent variable is labeled. So let's define the definite integral. So when I have a function and I know it's greater than 0, we're going to do scenarios where sometimes it's positive, sometimes it's negative. But for now, we're saying if our f of x is greater than 0, then the area under that curve, under the graph, can be expressed using our definite integral. So that area under the curve from a to b can be expressed by the definite integral from a to b of f of x dx. So let's see if we can put this into practice. We start small, folks, and then we kind of work our way up. So you'll notice here, the first question is saying, let's evaluate that definite integral from 3 to 7 of this function 6. That's a constant function, right? It's a horizontal line, it goes through 6. If I'm evaluating that from 3 to 7, well, that's just going to be the area under the curve of 6 from 3 to 7. That's just a rectangle. I know that this width, that base is 4, my height is 6, so that leaves us with 24. Here comes our calculator. So here is the one thing that we're going to be doing. We're going to be evaluating some of these definite integrals using our graphing calculator. So we're going to go to Math, and it's number 9. And hopefully you can see this. Zoom in a little bit. So what we can do with our calculators is we can put in the lower limit, the integral from 3 to 7 of 6, and then we just say with respect to x, it's always going to be dx. And our calculator is going to tell us what that definite integral is. If we look at the second example, we've got the definite integral from 0 to 8 of 3x. So that's the line y equals 3x. So this is a triangular region. So it's the same idea. I know that this length is 8. This one is 24. And so if I take 1/2, the product of the two legs, because it's a right triangle, that gives me 96. Again, if we go to Math 9 and type in 0 to 8, type in that function, it's going to tell us that that value is 96. Obviously, not all of our functions are going to be shapes that we know. But for now, we're going to be able to use our calculator to compute those values when needed. We'll also learn later how to do them by hand. But right now, we're using our calculators. So here is the big question. What do we do when our f of x isn't always positive? What if it's sometimes negative? So you'll notice here that when the areas are above the x-axis, we add them. when the areas of our curves fall below the x-axis, we subtract. So obviously the areas are always positive, but the definite integral takes into account the location. It's kind of like vectors, right? Where they measure length, magnitude, and direction. So the same follows with our definite integral. It's calculating what that area is, but also placement-wise, where is it on my coordinate plane? If it's below the x-axis, we subtract the area. If it's above, we add. So this, even this notation is weird, but we would say here, that definite integral would be negative a plus b minus c plus d. It's just written in that way. Let's have a look at this example. Here we have our definite integral, and this is our h of x, and we are given what those areas are for these specific intervals. So if we look at question 1, and they're asking us, what's the definite integral from a to b of h of x? A to b of h of x. I know that that area is 4. I also know that area is below the x-axis. So my definite integral would be negative 4. The area is 4, the definite integral is negative 4. Great. B to C, what are you thinking? The area is 18, it's above the x-axis. That is 18. So now for 3, they're asking what the definite integral is from A to C. So now we're looking at from A to B is negative 4, from B to C is 18. So I know that the definite integral from A to C equals 14. Lastly, think about what that absolute value is doing. I'll give you an example. We all know what the graph of x squared minus 4 looks like. It looks like this. If we were asked to graph the absolute value of x squared minus 4, that graph would look like so, because we're taking everything that was negative and boop, it's absolute value, right? So it's going to be positive. You don't have to think graphically about that, but I think sometimes that helps when we're looking at a question like 4. What is the definite integral from A to C of the absolute value of h of x? Well, then that means I'm thinking in terms of everything being above the x-axis. So that definite integral would equal 22. Don't lose sight of what the question is asking. For example, in this problem, it's asking me for the area of the region that lies above the curve y equals x squared minus 10 and below the x-axis. I know my graph looks like this. So what I need to do is figure out what those limits are. Where does that graph cut through my x-axis? And I know that that's going to be at plus and minus root 10. So folks, what I'm going to do now is use my calculator to find out what that area is. So let's go to the calc, and I'm going to go to Math 9. And you'll remember it was negative root 10 to root 10 of x squared minus 10. And you'll notice that they give me negative 42.164. Negative 42.164. But this question asked us for the area. It did not say what is the definite integral. So our answer would be that area is positive 42.164.